Our test is, what, next Monday? Monday, bright and early. So my plan today is to give you a very, very short lecture to finish up this one topic in chapter 33, and then to work out the sample test and answer any other questions you might have. So that's my purpose. So without further ado, let's take a look at the. Well, actually, before I take a look at that last little bit, let's do a quick review of what we covered last time in chapter 33. Chapter 33, we started looking at AC circuits, and part of the reason that we're dealing with the AC signals is that that's the way our power is generated. We turn a coil in a magnetic field, and that induces the electric current to flow. And that electric current alternates between positive and negative in a sinusoidal fashion. So we can describe the voltage induced by such a power as being equal to some maximum voltage times sine some angular frequency times time, where the angular frequency omega is the angular frequency that we're turning the coil with. And for that matter, current would equal some maximum current times sine omega t as well. There might be a phase difference, but basically that would describe the voltage and the current in the AC circuit. Once we make these definitions, and we can identify our maximum voltage and our maximum current as the coefficient out in front of the sine function, because the sine function can never be greater than 1. Then we can also say that we have what we call an RMS voltage, which is equal to our maximum voltage, divided by the square root of 2. These for a sinusoidal function, and that's the only kind of function that we're looking at in this chapter. So our RMS voltage is always going to be 0.707 times the maximum voltage. In other words, if you knew one, you could always get the other. And likewise, an RMS current is always equal to the maximum current divided by the square root of 2. And again, that would be 0.707 times the maximum current. Again, if you knew one, you could always get the other. If you knew the maximum current, you could get the RMS current, or vice versa. And once we define what is this RMS value, this root mean square value, then we can define what we call power. And power in an AC circuit is given by the RMS current squared times the resistance in that circuit. Later on in the chapter, we figured out what was impedance. And we said impedance is kind of like the overall opposition to the flow of current in the circuit. However, you would not put impedance in here because the only object, the only element in the circuit that's actually dissipating energy is the resistance. The other elements, inductors or capacitors, are storing energy. They store energy and give it back. So they're not dissipating power. They're storing energy, giving it back. So when we talk about power, we're only talking about resistance. So this is the formula you use. In relation to those other devices, we had what we called reactances, and we said the inductive reactance was equal to the angular frequency times the inductance. And that had units of ohms, just like resistance. Of course, it's not resistance because you're not dissipating energy like we just said, but it does represent in opposition to the flow of current in that circuit. It provides opposition to the flow. So in a sense, it acts like resistance in that sense, as an opposition to the flow. The reason it opposes the flow is because the flow of current is being diverted in a sense to supply the magnetic field of the inductor. And then that energy will be given back again. So that's inductive reactance. Then we have capacitive reactance, which is 1 over omega times C. And when you multiply radians per second times farads, and you take 1 over that, you get ohms. So that has units of ohms as well. Ohms and ohms, just like resistance. But they are not resistances, they are the opposition to the flow of current. Now, the reason this opposes flow is because we are storing energy in the capacitor, electrical energy, in the electric field of the capacitor, and we're going to give that back to the circuit. So, the last thing we did was to figure out impedance. Z. Impedance was equal to our total resistance in the circuit squared plus our total reactance in the circuit squared square root, where we define our net reactance as the inductive reactance minus the capacitive reactance. This minus this. The reason it takes this form of a Pythagorean form is because they're out of phase by 90 degrees. So you got the resistance, which is in phase with the current. We got the reactance, which is 90 degrees out of phase with the current. And so in order to find the impedance, we have to use a Pythagorean theorem type relationship. And I think that's it. Right, basically. If you use this, you can use this on any of the circuits that we're going to look at in AC circuits. Okay? This will always apply. Now, I know we did some individual circuits where we just had maybe one capacitance or one inductance, and then we figured out the inductive reactance, and we said, that acts like an ohm-like relationship. But the only reason we went straight to this is because these are subsets of this. In other words, if we don't have any other elements in there, if we don't have resistance in there, then our impedance will be the reactances. But this works all the time. All right, so that's basically what we did last time. And today I'm just going to give you just a couple more things, not too much, because I want to spend most of the time working out the sample case. So I'm going to skip the parallel RLC circuit. And also I'm going to skip the use of complex numbers I introduced there. That's good for a complete treatment. If you take AC circuits later on, you're going to want to know that stuff. But at least it's there, and you can look at it in the notes. We're going to skip the complex numbers. We're using of J as a complex number. And I'm going to skip the parallel RLC circuit. Just want to show you this because it's something that comes up, kind of interesting application of RLC circuits. Resonance. Say you have an RLC circuit and you've got this resistor, and capacitor, inductor in this circuit. As I said before, the inductor and the capacitor represent opposition to the flow of current, but the reason they represent opposition is because they're storing energy in their respective devices and giving it back to the circuit. Well, there might be a point where when they're giving the energy back to the circuit, they start giving the energy back and forth between each other. And there would be a characteristic frequency at which that might occur when they start giving back this energy back and forth between each other. In other words, they might resonate in that circuit between each other. And hence there would be a definite resonant frequency for that to occur, for resonance to occur in that circuit. That resonant frequency would correspond to when the inductive reactance is equal to the capacitive reactance. Another way to look at it is this. Your root mean squared current is equal to your root mean squared voltage divided by your impedance. But your impedance is going to be the square root of R squared plus your net reactance squared, which is the inductive reactance minus the capacitive reactance. And we'll see that this would be maximum. In other words, your current will be maximum when the inductive reactance equals the capacitive reactance. Because if these two quantities were equal, then this difference would be 0, and hence your denominator would be at its least value it could possibly be, which means that the fraction of RMS voltage over that will be at its greatest value it could possibly be. In other words, we'll get the best possible maximum current we can possibly get, which is simply the RMS voltage divided by the resistance. In essence, the capacitor and the inductor, their reactances would cancel out. And you would get a resonance in your current. If I were to graph this, it might look something like this. I'm graphing the current as a function of frequency, and it would peak out at some value, and on either side of that, it would rapidly drop off. So you would have a maximum value resonance of the current occurring when the reactances were equal. Now, if the two reactances are equal, then it's true that omega L would equal 1 over omega C. And solving for that particular angular frequency where that occurs, we have that the angular frequency is equal to 1 over the square root of inductance times capacitance, which means that that is our resonant angular frequency. We will have a resonance in this AC circuit when the angular frequency is equal to 1 over the square root of L times C. And some of you did the last experiment 11 was a makeup, and that was the case. Right? We did the LRC circuit, and we found that there was a resonance when your frequency was equal to this. Well, what could this be good for? If you're creating a resonance in a circuit, an AC circuit, you could set up a circuit as a tuner, and you could basically have it resonate at a particular airwave frequency in order to, in a sense, enhance that frequency and pick up that frequency and magnify it so that you can listen to that frequency. So, say if someone's sending you radio waves and you have an AC circuit, if you can resonate your circuit at the frequency of the radio waves, you can pick up that radio wave, acts as a tuner, bring in that signal. Right? So by turning the dial on a radio, what you're doing is basically either changing the inductance or the capacitance of that circuit on your radio so that you're changing your resonant frequency, and hence you pick up a different frequency. How would you change the inductance or capacitance in that circuit? You could do it like this. got an inductor, say at the core, you know that if you move the core in the inductor, you can change the inductance. Right? If there was no core, we did an experiment on that. No core was 8.2 millihenries, the core was 33 millihenries. So the core has a big difference on the value of the inductance. So if you just move that core in and out, this is rather simplistic here. If you just move that core in and out, you could change the inductance, change your resonant frequency of that circuit. Or, we know from chapter 26 that the capacitance depends on its spacing between the plates. So if you just move the plates in and around, you would change the capacitance, change your resonant frequency, resonate at a different frequency. Some very simple radio receivers have this kind of concept with them. And just real simple receivers that you could probably build with materials around the house. Here's another application. We know that this circuit will resonate at a particular frequency, and so if you were to change the inductance at all, then this current will drop off on either end. In other words, if you had already tuned your circuit to a particular frequency with a particular inductance and capacitance, if one of those values were to change just a little bit, then your circuit will drop off to maximum resonance rapidly on either side. So you would know when that change occurred. Let's try this. Let's set up our RLC circuit like this. We have a source, we have a resistor, we have a capacitor, and we have a coil. Right? So our coil happens to look like a door, except that it's a big coil. All right? In essence, there's a big inductor. Right? And you have expertly tuned your circuit so that you are at maximum current for this well-tuned RLC circuit. So that if either of these values were to change just a little bit, your current is going to drop off on either end of this resonance. Along comes somebody, and they happen to have some metal in their pockets. Right? That metal changes the inductance of this coil, and the current drops off from maximum, and you know it. Right? You probably put in a bell there, that if the current drops off below a certain value, the bell will ring, and you detect that this person has metal on it. Here's another one. Still resonance. Set up a circuit with a resistance, capacitance, and an AC source. And now we're going to put the coil underneath the road, or at least near the road, maybe. And along comes a car. And it doesn't have to be in the coil, but in the presence near the coil, it can change the inductance of that coil. And again, that will change the inductance in your circuit, change your resonant frequency, drop off from maximum, bell goes off, and the traffic light immediately turns for you. Unless you go to this one over here near the gas station.
Watching their live lot doesn't help.
Probably not. Unless it has a different kind of sensor. Maybe other sensors and more modern traffic light sensors. And they might have light sensors. But this is the style that I'm most familiar with. Let's try an example. Here's an RLC circuit used in a radio to tune to an FM station broadcasting at 99.7 megahertz. The resistance in the circuit is 12 ohms. The inductance is 1.4 microhenries. What capacitance should be used? Well, we want to tune this circuit to 99.7 megahertz. Angular frequency then would be 2 pi times that frequency. 2 pi times 99.7 times 10 to the 6. 6.26 times 10 to the 8 per second. We want to find a capacitance that will resonate the circuit at the desired frequency, at this desired angular frequency. And that would be the angular frequency is equal to 1 over the square root of the inductance times capacitance. Solve this for C, square both sides. Bring C over here and bring omega squared down here. So we have the capacitance we need is 1 over the inductance times omega squared. 1 over 1.4 times 10 to the minus 6 Henry and 6.26 times 10 to the 8 radians per second squared is 1.82 times 10 to the minus 12 farads, or 1.82 picofarads. And we can do it. So there's your rating. One more section in this chapter is on transformers, and actually I'm going to cut this section out because we need to focus on, we need to go over these problems. I'm not sure I got enough time, so I'm going to cut this section out. But I just want to say one thing about transformers. Well, actually. Transformers are more than meets the eye. They're kind of cool. You start off with this car, and then things kind of move around, and you end up with a crime-fighting superhero. So they definitely are more than meets the eye. But we don't have time to go into this anymore, so we'll just kind of leave it at that. But again. Transformers aren't really that bad. I mean, the electrical transformers. So, I'm going to start on the sample test. We'll start with problem number 1. Anybody else need a sample test? The first problem is a Biot-Savart law problem from chapter 30. There's some point P here, and we have a current coming in into P, and it goes through this curvature here, and then it comes out over here. And the current is equal to 3 amps. This curvature is equal to 2 centimeters. And the question is, determine the magnitude and direction of the magnetic field at point P, at the center of that curvature. Biot-Savart law. So what should I do?
Split up into segments,
Split up into segments 1, 2, and 3. Correct. So we'll split it up into 3 segments. Look at the result for all 3 segments, and then superimpose the results together. So if we look at segment number 1, where we've got this line coming in here, and P over here. the magnetic field at point P to segment number 1? 0. Magnetic field is 0 because we are off the end of that current segment. So if you're off the end of the current segment, magnetic field is 0. So far, so good. We look at segment number 2. R is 2 centimeters or 0.02 meters. And we're looking at this segment right here. We have a curved segment, and we have a formula for that. So V2 is going to be mu naught I over 4 pi r times theta, where r is the radius of our curvature, and theta is our angle. So this will be 4 pi times 10 to the minus 7 times 3 amps over 4 pi times 2 centimeters or 0.02 meters times theta, our angle, which is what? Pi over 2. Do not put in 90 degrees. Yes, from the unit circle. You have, you go all the way around the circle, all the way around is 2 pi. And if you go halfway around, it's pi. If you go a quarter of the way around, it's pi over 2. So we just have pi over 2, quarter of the way around. So we have, let's see. I got 2.36 times 10 to the minus 5. Tesla. Into or out of the page? Well, let's see. Current's going down this way. So use the right-hand rule. You're right. It's out of the page. Out of the page. Everything on this side with the right-hand rule will be out of the page. And I caution you now, when you're taking this test, and you will have to use the right-hand rule on this test, to indeed use the right-hand rule. So even though you write right-handed, most of you write right-handed, you're going to have to put the pencil down and do the right-hand rule. So you can't do both. You can't multitask during this test. Right? And I've seen it many times. People are doing the right-hand rule with the left hand when they're trying to write. And that would just reverse your answers. So don't do that. So last thing is the segment 3. And we've got the segment that's coming out like this. Here's point P. It almost looked, at least at first glance, it might look like it's off the end, but it's not. Right? Because we're actually removed some distance from the line of the current. And in fact, the distance that we're removed is actually equal to R. So we're just interested in this pure perpendicular distance from the line of the current to that point. And so we do have a Biot-Savart formula for this. We have, in this case, U3 would equal mu naught I, 4 pi r, times the cosine of theta 1 times the cosine of theta 2. So theta 1 is the first angle from the current direction and the vector to the point. So that, in other words, in this case, that would be theta 1, the first lead angle of the direction of the current and the vector that points to the point from that end of the current. And theta 2 is from the direction of the current and the vector that leads to the point. So way over here somewhere, theta 2 at that end. All right? If you go infinitely far this way. All right? This is a semi-infinitely long wire. So, U naught is 4 pi times 10 minus 7. Current is 3 amps. Radius, or distance from the current direction, is 2 centimeters. And we'll have cosine. Really, in this case, it won't matter whether you put 90 or pi over 2, because you take the cosine of it. So I'll just put it 90 degrees. Minus the cosine of, what's the other lead angle? 180. 180. It's going to be 180. If I go semi-infinitely along this way, I'm going to end up looking at this angle right here, which will be 180 degrees. Cosine of 90 is 0. Cosine of 180 is negative 1. So we have a negative, negative 1, which is positive 1. So it'd be 3 times 10 to the minus 7 over 2 times 10 to the minus 2. This would be 1.5 times 10 to the minus 5. That's not. Into or out of the page? Into the page. The right hand rule. Everything above this current will be into the page. Everything below it will be out of the page. You can imagine that there's a magnetic field around this wire like this by the right hand rule. So everything up here is going to be into, especially at point P, and everything down here is out. So this one's in. So we want to find the net magnetic field at point P. We have 3 of them. The one of them's in, the one of them's out. It looks like the one that's going out is larger than the one that's going in. So our net magnetic field is going to be the sum of these 3, at least vectorially. And in terms of magnitude, then, that's going to equal 0 plus 2.36 times 10 to the minus 5 minus 1.5 times 10 to the minus 5. If we think of our net field as coming out, and so this is going to be 0.86 times 10 to the minus 5 or 8.6 times 10 to the minus 6 Tesla out of the page. Sound good? Yes.
You said segment 3 was almost like an infinitely long piece of wire. Did we not use that formula for an infinite piece of long piece of wire as well?
I stuck a little prefix in there. It's semi-infinite. Semi-infinite. It's infinitely long in this direction, but it cuts off right there. semi-infinite, if there's such a thing.
Can you explain why we can use the 90 degrees and the 90 degrees over here, but we can't use it over here?
Yes. Because if I put the angle inside the function, the cosine function, then the function is just working on the angle. So it doesn't matter. The only thing that matters is that you have your calculator in the right angular form. You know, I mean, if you're in radians mode and you want to put radians in here, why you do the cosine on something. Or if you're in degrees mode, you want to have degrees in here, why you take the cosines. But here the angle is all by itself. So the angular is what you're going to get, right? So you have to use the radians mode on this because that's what's set up, designed for.
So we can just make it a rule of thumb and just use radians alone.
That would be the safest way, is just to make sure you use radians on everything. Right? Put your calculator in radians mode, and that would be the safest thing to do.
So we just do sine of pi over 2 and sine of pi.
Right. That's what
I mean, cosine.
cosine of pi over 2 is what it is. Cosine of pi. Okay, let's take a look at problem number 2. Because a 20 ohm square loop is placed in a uniform 0.2 Tesla magnetic field directed perpendicular to the plane of the loop into the page. The square loop is then reshaped into a circle with the same total length. If the process takes 0.3 seconds, what is the average current generated in the loop? So we have a square loop, 2 meters on the side, and the resistance of this loop is 20 ohms, and we're going to place it in a magnetic field, and the magnitude of that magnetic field is 0.2 Tesla, and the magnetic field is directed into the page. So we assume that there's a magnetic field into the page of this loop. And we're going to take this loop, and we're going to reshape it into a circle. So we can go, we're just going to bend the wire into a circle, all the while being inside this magnetic field that's going into the board. And the question is, if we do that in 0.3 seconds, what kind of current will we generate? Well, according to Faraday's law, one aspect of it, the average EMF induced is going to equal, at least the magnitude, the number of turns times the change in flux, or the change in time. I'm not going to worry about the minus sign because we're going to account for that using Lenz's law next. Let's just look at this. In this case, we only have one turn, so n is 1. But the flux is going to be the field times the area. And the area is changing, the field is not. So I can write this as the change in the field times the area per time. That's just going to be equal to the field times the change in area per time. Angle's not changing, so we don't have to worry about the cosine theta. The cosine theta was 1. So, the question is then, what is our area? Because our delta t was given as 0.3 seconds. We're going to do all this in 0.3 seconds. And we know the field, so we just need to know find the change in area. Well, our original area is the area of this square. So our initial area is going to be 2 squared, or 4 square meters. What's our final area? I always save the hardest question. How can I find the final area of this loop?
You take the circumference and find the radius of the circle, and then you find the area.
Exactly. What is going to stay constant is the circumference, the perimeter of this object. The perimeter here is 8 meters long. And when I bend this into a circle, the perimeter will still be 8 meters long. Right? I can use that to figure out the radius of the circle, and then I can find the area of the circle by pi r squared. So that's my plan. So let's do that. The circumference of this circle then should be equal to 8 meters. And by definition, the circumference of a circle is 2 pi r. So the radius of this circle is going to equal 8 divided by 2 pi. .27 meters. And now we can find the area of that circle. Area is going to equal pi r squared. So pi times 1.27 squared is 5.09 meters squared. So actually that will be our final area. That will be the area of the circle. So our change in area is going to be the final area minus the initial area. 5.09 minus 4, or 1.09 square meters. And hence our induced voltage, our induced EMF, will be equal to field times the change in area over the change in time. 0.2 1.09 over 0.3. Get 0.729 volts. At least that's the induced voltage, the induced EMF. But part A is asking for the average current induced. So we've got the induced voltage, we know the resistance. So the average current induced is going to equal the induced voltage divided by the resistance. 0.729 volts divided by 20 ohms. Is 0.0364 amps. Or I guess that would be 36.4 milliamps. So kind of neat. You got this uniform magnetic field that's set up. You got a little wire in the square. Just bend the wire or the square into a circle and you're generating current. Just changing the shape of the wire. Of course, my next question is, in what direction in that wire is the current going to flow? Well, in order to determine that, I'm going to go through that hierarchy of questions that I've asked you to use in this situation. And the first question is always, what is the direction of the original flux? And the direction of the original flux is the same direction as the original field, which would be, in this case, into the board. So our original flux is into the board, at least as we've drawn it. Second question is, what is the second question? And you can put these questions on your 5x7 page, 4x6 card. Is the flux increasing or decreasing as we proceed through this problem? Flux is field times area times cosine of the angle between the two. In this case, we had no angle to worry about. As we proceed through this problem, as you change this from a square into a circle, is the flux increasing or decreasing? Increasing. Because the area is increasing. Right. Field, everything else being the same, area is increasing, so the flux is increasing. All right. So that describes what's happening. That's what's going on. Flux is into the board and it's increasing. Now we're ready to think about what's going to happen in the induced current and induced field. If nature has this flux that's into the board and it's increasing, how is nature going to respond to that? It wants to create its own flux out of the board against that. So the induced flux is out, which basically would mean that the induced field is out. The last question is, what current, by the right-hand rule, would produce that induced field out of the board? Counterclockwise. So I induced, and it's counterclockwise. By the right-hand rule. Let's go in counterclockwise. So far, so good? Take a look at problem number 3. Consider the circuit shown at left. What's the value of the current 1 second after the switch is closed? What energy is stored in the inductor when the current reaches its final equilibrium value after the switch is closed? A 4 Henry inductor, 8 ohm resistor, and a switch, 0.4 volt battery. And the fact that we have a switch means that you're immediately thinking LR circuit, right? Not AC circuit, because you got a DC battery there, right? You're thinking LR circuit. So you're not going to do chapter 33 stuff on this. You're going to do chapter 32 stuff. It has a switch and it has a battery, not an AC source. That would be your key. So the question is, what's the value of the current 1 second after the switch? For such a problem, I'd like to know the time constant and the maximum current. The time constant is L over R. That'll be 4 over 8, 25 seconds. So in 0.5 seconds, the current will reach 63.2% of its final value. The maximum current will equal the voltage of the battery divided by the resistance. 24 volts divided by 8 ohms, or 3 amps. So this current will go up to 3 amps and go no more. The current for all time is going to equal to the maximum current of 1 minus e to the negative time over the time constant, e to the negative t over tau. Now I put these values in, and I have the current for all time is equal to 3 times 1 minus e to the negative t over 0.5. 1 over 0.5 is 2, so this is 3 times 1 minus e to the negative 2 times time. That is the current for all time after we close that switch. The question was, what is the current 1 second after we close the switch? So if we want to find it at a particular time, where t is equal to 1 second, then we'll just plug in 1 second there and see what it is. So at t equal to 1 second, current is equal to 3 times 1 minus e to the negative 2 times 1. And I get 2.59. If you're not familiar with using the exponential function, you probably want to get familiar with it. We're not trying to do that on the test. So make sure you come up with the same answer. Does that make sense? So the time constant was 0.5 seconds. So we should have reached 63.2% of this final value, 3 amps, in 0.5 seconds. However, the time we're talking here was 1 second, so it was actually 2 time constants. All right? So we actually went, we should go more than 60% of this, and we did. Right? Actually 60%, 60%. Good. So it makes sense. We're beyond that point. What energy is stored in the inductor when the current reaches its final equilibrium value after the switch is closed? Energy is 1/2 the inductance times the current squared. In this case, we want to use the current, the final equilibrium current, which is the maximum current. When the switch has been closed a long time, then the inductor, the current will stop to change after a while, and the inductor will have no voltage, and your current will simply be this, 3 amps, after a long time. So this would be 1/2 times 4, that's 3 squared. That's 2 times 9, 18 joules. So that is the energy stored in this inductor when the current has reached its final equilibrium value. Problem number 4. Parallel conductors carry current in opposite directions as shown in the figure at left. One conductor carries a current of 6 amps. Point A is at the midpoint between the wires, and point C is at a distance d to the right of the 6 amp current. If d is equal to 10 centimeters and I is adjusted so that the magnetic field at C is 0, find the value of the current I. Two wires, we'll say I2 is 6 amps going up like that. And we'll say I1 is this current, which we don't know what it is. Here's point A, midway between the wires. And the distance between the wires is D. And here's point C over here, which is also a distance D away from the second wire. And D is 10 centimeters, or 0.1 meters. And the question is, if we were to adjust the current in wire 1 such that the magnetic field at C is 0, then what is that current that will do that? Well, we have two infinitely long wires. We know the magnetic field due to an infinitely long wire is mu naught I over 2 pi r. If we are some distance, perpendicular distance r away from that wire, an infinitely long wire. If I look at wire number 1, using the right-hand rule, pointing in the direction of that current, everything to the right of this wire is going to be out of the page towards you, and everything to the left of this wire will be into the page away from you. So in the vicinity of C, there's going to be a magnetic field, it's called B1, that will be out of the page towards you. If I look at wire number 2, by the right-hand rule, when the current goes like this, everything to the right of this wire will be into the page. Everything to the left of this wire will be out of the page. So in the vicinity of C, there will be another field, it's called B2, that will be into the page. It's possible that the magnitude of these two fields were equal. Those two fields would cancel out. They're in opposite directions. So we could possibly get no field at point C if the magnitude of these two fields were equal. So let's try that. Let's say that B1 equals B2. And then hence we would get no field at point C due to the direction. So that means mu naught I1 over 2 pi R1 would equal mu naught I2 over 2 pi R2, at least in magnitude. Well, I'll solve this for I1. I can get rid of a mu naught on both sides. I can get rid of a 2 pi on both sides. And solving for I1, I have I1 is equal to R1 divided by R2 times current I2. R1 is the pure distance that we are away from wire number 1, which is actually going to be 2D. So 1, 2. And R2 is just going to be D. So this is going to be 2D over D times I2. 2 times 6 or 12.
We have seen that right off the bat, that it should be 2 times the I2 over 4 times
What do they say? Faith without works, and you're a goner, right? That's your work. Physics without work, and you're a goner. where's the value of the magnetic field at point A? Still over here. Let's take a look at point A. Point A, we've got a magnetic field coming out of the board due to wire number 1. Due to wire number 2, we've got a field also coming out of the board from the right-hand row. So both fields here are out of the board in the same direction towards you. So those two fields are going to add. Let's find the magnitude of those two fields at point A. We've got field number 1, which would be mu naught I1 over 2 pi R1. That's going to be 4 pi times 10 minus 7 times 12 amps, which we just determined, over 2 pi. Our distance to A is going to be what? 0.05. Because we're going to be half of D. So this is .8 times 10 minus 5 Tesla. Is that good? Is that good? And that would be out of the page. If we look at the other magnetic field, same sort of thing, mu naught current 2 over 2 pi R2. So this is 4 pi times 10 minus 7 times 6 amps over 2 pi. We're still the same distance away at 0.5. And just doing that calculation in my head, 2.4 10 minus 5. Quickly, and carry the 2 by pi. Carrying pi out to 7 decimal. So it's a little bit inaccurate. So both of those are in the same direction. So our total field is going to be 4.8 times 10 minus 5 plus 2.4 times 10 minus 5, or 7.2 times 10 minus 5 Tesla. Out of the page. At 0.8. Part C, what is the force per length between the wires? There's a formula for that. Looks like this. Force per length is equal to mu naught current 1 times current 2 over 2 pi d, where d is the actual distance between the wires. So the force per length in this case would be 4 pi times 10 minus 7. Our famous mu naught constant times 12 times 6 over 2 pi times d, which is 0.1. 0.44 times 10 minus 4. Newton per meter. On number 5. This is a 50 millihenry inductor is connected in series with a 200 ohm resistor, a 6 microfarad capacitor, and a 60 hertz source with a voltage of 210 volts sine omega t. Calculate the capacitive reactance, the inductive reactance, the impedance, the RMS current, and is the circuit more capacitive or inductive? And the capacitor over here, 6 microfarads, 200 ohm resistor, 50 millihenry inductor, and an AC source. Our source has a maximum voltage of 210 volts. Frequency of 60 hertz. The actual order of these circuit elements doesn't really matter. So you can have these RLCs anywhere in the circuit. The voltage actually was described in the problem like this, 210 sine omega t. So if you were given that in the problem, you would recognize that up front, that's your maximum voltage. So you could get that right away from that. We're told that the source is 60 hertz, so omega is 2 pi times the frequency of the source, 2 pi times 60, or 377 per second. So the first thing is find the passive reactance. Passive reactance is 1 over omega times c. That's 1 over 377 times 6 microfarads. And what is that? .42 ohms. So that's our passive reactance. What is the inductive reactance? That by definition is angular frequency times inductance, so L. So that'll be 377 times 50 millihenries. And if I do that, I get 18.85, about 18.9 ohms. So right away, I can answer part E. Is the circuit more capacitive or inductive? Well, since the capacitive reactance is larger than the inductive reactance, it is more capacitive. So let's do that. Since the passive reactance is greater than the inductive reactance, it's more capacitive. Part C, what is the impedance? Well, we can find our net reactance. That's going to be the inductive reactance minus the capacitive reactance. So our net reactance is this. And that would be 18.9 minus 442.1. Should be able to do that in my head, but minus 423.3 or 0.2. And our impedance by definition is the resistance squared plus the net reactance squared. Square root. So our resistance is 200 ohms. That'll be 200 squared plus negative 423.2 squared, square root. The fact that that's negative is not going to matter because when you square it, it's going to be a positive quantity. I get 468.1 ohms for our Z, for our impedance on this circuit. We want to find the RMS current. I have room down here, John. Can you see that? RMS current, well, we don't have room. We've got to do two things. So I'm going to move over here. We have to find RMS voltage. We have the maximum voltage. This V max is 210 volts. V RMS is V max divided by the square root of 2. So that's 210 divided by the square root of 2. It's 148.5 volts. RMS. And so the RMS current is the RMS voltage divided by the impedance. That's 148.5 volts divided by 468.1 ohms. And then 0.317 amps. RMS. Kind of plug and chug, straightforward stuff, right? So I'm hoping, if you get a problem like this, you just start plugging away. You'll be happy to see this problem, right? Take a look at problem number 6. 100 millihenry inductor is connected in series with a 500 ohm resistor, a 100 microfarad capacitor, and a 50 hertz 100 volt RMS source. Find the RMS current in this circuit. So we have a 100 microfarad capacitor, and a 500 ohm resistor. And we have a 100 millihenry inductor. And all this has a source, AC source, with RMS voltage of 100 volts and a frequency of 50 hertz. first question is, what's the RMS current in this circuit? We know the RMS voltage. That's given already. So if I knew the impedance, then I could find the RMS current. It's like up here. So I need to find the impedance. In other words, I have to do everything I did in the last problem for part A on this one. Yeah. So the first thing is find omega. Omega is 2 pi f. That's 2 pi times 50, or 314 per second. So we might be in Europe on this one. We want to find the inductive reactance and the capacitive reactance. The inductive reactance is omega times L. So that's 314 times 100 millihenries. 100 times 10 to the minus 3. That's going to be 314 times 0.1, which would be 31.4 ohms. Passive reactance is 1 over omega times C, and that would be 1 over 314 times 100 microfarads. If I figure out that, I get 31.85 ohms. This particular circuit is very, very close to resonance. Right? The two reactances are very close to each other. So it's very. This is probably a well-tuned circuit. Our net reactance is the inductive minus the capacitive reactance. 31.4. That's 31.85. Will give us a negative 0.45 ohm in the net reactance. And hence, our impedance is the resistance squared plus the net reactance squared, square root. And that is going to be 500 squared plus a negative 0.45 squared, square root. I'm just kind of doing that in my head. 500 squared plus square root 33. That's about 500 ohm. Impressed? So it is pretty close to resonance. So the actual impedance is actually equal to the resistance of the circuit. We still have to find the RMS current. I RMS and VRMS divided by the impedance. That is going to be 100 volts divided by 500 ohms, or 0.2 amps RMS. We want to find the voltage drop across the inductor. It says use RMS current. So if you're asked for the voltage drop across anything, please use the RMS current. What we need to do to find the voltage drop across something is, in particular, for the inductor, that would be the RMS current times the inductive reactance. Just to find the voltage drop. So you treat the inductive reactance in essence as its counterpart to resistance in an Ohm's law type relationship. But it's not Ohm's law. but it looks like 120. I times the inductive reactance. So this will be 0.2 times 31.4, and that is 6.28. What is the voltage drop across the capacitor? Same sort of thing. Voltage drop across the capacitor is the RMS current times the capacitor reactance. That's going to be 0.2 times 31.85. So that would be 6.37. What is the power dissipated in this circuit? Power is the RMS current squared times what? Resistance. Not impedance, but resistance. So this will be 0.2 squared times 500. What is that, 20? 20 watts. Good? Real good? Those are brief characteristic problems for this chapter 33. We have one last problem to look at. Problem number 7. Use Lenz's law to answer the following questions concerning the direction of induced currents. What is the direction of the induced current in resistor R in the figure below when the bar magnet is moved to the left? We have a bar magnet that looks like this, moving this way. And we have a coil over here, a solenoid, if you will, and the windings look like this. And they're coming down through a resistor over here. And the question is, they're not connected electrically in any way, but the question is, if I move that magnet to the left, what direction will the induced current flow through R, through that resistor? To answer this, we're going to go through those hierarchy of questions that you're going to have somewhere on your 2x3 card. 3x4, 4x6. 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 Okay. First question would be, what is the direction of the original flux? The original flux is always the direction of the original field. And we're interested in what is the original field, the original flux in the vicinity of this item that we're going to analyze here is the solenoid. Well, this thing is moving to the left, but as far as the flux is concerned, it's dominated by the magnet. What is the magnet doing? What's the orientation of the magnet? And for magnets, flux lines come out of north poles and they go into south poles. So the flux lines, magnetic flux lines of this, are coming out over here, coming in over here. To answer this first question, what is the direction of the original flux? You need only look at this. Then in the vicinity of this coil, we've got flux lines that are going from left to right. So the direction of the original flux is left to right. in the direction of these lines coming out of the road flow. Second question. As we proceed through this problem, does that flux increase or decrease?
Decrease.
This one is decreasing because the magnet's getting further away. And the magnet's moving this way. So that flux is in that direction, but it's getting weaker. So flux is decreasing. Now we're ready to focus in on this, forget about the magnet, and see what's happening over here. This situation over here is experiencing a flux. The flux is in this direction, but it's decreasing. To oppose that change, to try to maintain the status quo, there will be an induced flux in that same direction to try to supplement and try to maintain things at a constant level. So, question 3 is, what is the direction of the induced flux, the induced field? And we'll say that B induced is left to right. It'll be like that, to the right. Your answer to this will always be the same as your answer to 1 if your answer to 2 is decreasing. Okay? If you say decreasing here, this will be the same as this. If you say increasing here, this will be exactly opposite of this. So you don't have to think.
Make sure the ones are
You have to make sure you get 1 and 2 right. That's right. And then it should flow. So we've got an induced field that's going this way through the middle of the solenoid. Question 4 is, what current will help produce this field? And if I look at a solenoid and apply the right-hand rule for a solenoid, you will have a magnetic field through the center of the solenoid from left to right if the current in your windings are coming down, as we see it. So the current would have to be coming down this way through the windings. So I induced is down through the windings. This particular problem may have a 5th question because the question was, what is the direction of the current through R? Now, if this current is coming down through the windings, you kind of have to look at your diagram to see where your last winding is. And this one has its last winding over here on the right. So it's coming down through that one, which means it must be going right to left to the resistor. So I induced is right to left through the resistor. I don't think there's any shortcut to do this. You have to think it through like that. Either that or just flip a coin and maybe half crack maybe. B, what is the direction of the induced current in R when the current I decreases rapidly to 0? We have a current going like this. We have a separate loop over here. And we're going to go through that same hierarchy of questions. First question is, what's the direction of the original flux? Well, that's due to this current coming down like this, and in the vicinity of that coil, it's coming out of the page. So, the flux is out of the page towards you. Second question. As we proceed through this problem, does that flux increase or decrease? Decrease because the current is decreasing rapidly to 0. So flux decreasing. So without thinking, I could say that B induced is out of the page. And if I did think, it would make sense that it should be, because you got a flux out of the page is decreasing. Nature wants to supplement it to keep it going out of the page. So I induced is
To left.
from right to left through that resistor, counterclockwise through the loop. So I induced is counterclockwise. From this way. And that means it would be right to left through the resistor. I think this is a good representative sample test, but if you need more practice, I would do the problems in the homework. If you need more practice, I would do all the problems in the book. If you need more practice, I would go to the library and find more physics books and do all the problems in those. Go online, use the internet, find problems on the internet. We skipped 32. What problems in chapter 33? I would do these circus problems. These problems here. We did number 16 the other day, but those would be good practice for. There's kind of similar to the sample test problem.